My presentation. Start again. Okay, so can you see the presentation? Can you see the screen?
Yes.
Yes.
Okay, this is where we stopped last time, I believe. We started looking at Verilog. We saw a brief history about Verilog and how it came about. And so in this section, what we're going to see is various, first of all, how do you design combinational circuits using Verilog? How do you design sequential circuits using Verilog? And how do you design something called finite state machines using Verilog? Using Verilog, there could be mainly two modeling techniques or design techniques. One is a structural modeling, the second is RTL modeling. RTL modeling sometimes, earlier it was called RTL modeling, nowadays it's called HDL modeling or behavioral modeling. Mostly the term that is used nowadays is behavioral modeling. It's the same thing. We'll see what that means in the upcoming slides. Um, Before we proceed, any questions that you might have till now? Do you guys have any
No.
questions? No questions?
No.
Okay. So there are two things that are required for functionality of hardware. First thing is concurrency. Concurrency means parallel execution of logic. And the second thing is timing control. So digital logic design, whatever you do, whatever you design, will need a lot of timing control over the design. So timing control could be mostly is related to clock. So anything that works in digital logic design, when it is synchronous, it's synchronous with respect to clock, which is a common signal for all the circuits or all the sections of the circuits. So these are two key things that are required for functionality of hardware: concurrency and timing control. An implementation of the hardware can be in a netlist format or a structural format, which is in netlist format, or it can be behavioral description, which is in the RTL format, registered transfer language. So before Verilog and VHDL were called HDL, which is HDL stands for hardware description language. They were called RTLs, registered transfer level languages. Later on, everything was basically, and there were a lot of languages earlier, which were mostly proprietary, company based. Later on, it got standardized to two languages, Verilog and VHDL, and they were called HDLs, hardware description languages. So design can be represented at various levels. Just hold on 1 second. Let me see if I can pull this down. Okay, okay. So a design can be represented at various abstraction levels. The bottommost abstraction level is a switch level or a transistor level. Ultimately, everything on a chip works at a transistor level, and in this case, CMOS transistor level. One level abstraction above transistor level representation is gate level design. So beyond, so above CMOS level, gate level is basic gates. It could be the basic primitive gates like AND gate, NOR gate, etc. Or it could be some other basic gates like combinational circuits. Could be adders, subtractors, and other things. Or it could be sequential circuits like latches, flip flops, etc. So that's the next level of abstraction that a design can be represented in. One level above, one abstraction level above is where we operate at a very low level, RTL or HDL level. At a RTL or HDL level, it is what we do is a text-based description. It's a language. So in the language Verilog or VHDL, to describe our design, the design could consist of data flow section, control section, storage elements like memories, and obviously clocks. Right? So those are that is the abstraction level above gate level. Bottommost switch level, gate level, Verilog level. And one level above that which is where the industry is trying to operate at currently, or they're trying to develop a language, is algorithmic level. It is called high. You might have heard terms like high-level synthesis or ESL, electronic system level language. Have anybody, if any one of you use MATLAB in your undergrad or post or your grad curriculum anytime?
Little bit, not very much.
Sorry,
Yeah, just a little bit.
just an overview, right? But you know about
Yeah.
MATLAB. So
Yes.
MATLAB is
Mm.
something where we can develop algorithms rather easily. I mean, that is just one example of a language. You could use Python or some other programming language also, high-level programming language. So that is where there is some examples of languages, Python or MATLAB, for example, where you can develop algorithms relatively easily. Algorithms can be represented using equations, right? So you develop algorithm. When you develop an algorithm, you develop various equations, and there is a flow of equations, and then slowly you develop step by step the equations are executed, and you develop an algorithm out of it. So that level of abstraction happens at algorithmic level. So that level of abstraction is still not possible with Verilog. I cannot feed Verilog. I cannot just write one equation in Verilog or a set of equations in Verilog and say, for example, implement my digital filter design. I cannot tell the synthesis tool that this is a set of equations. Now implement my digital filter design or some other algorithm, some other encryption algorithm or something like that. I can build that algorithm in Verilog, but then what I have to do is take the equations at the algorithmic level, break down the equations in smaller parts, and then build those smaller parts using the digital logic circuit in Verilog. Then I can implement my algorithm. So one level above Verilog is algorithmic level, where is still the industry is still trying to develop a language where I can represent that. Then ultimately, it will go down from algorithmic level to gate level to switch level, and will work on the chip. So the effort is going on to do that, but we are not there yet. So we work basically at the RTL level or Verilog language construction. Okay.
Yeah.
Okay.
Structural, so Verilog design or digital design can be represented in Verilog in two formats, structural and behavioral format. What does the structural format consist of? It's a netlist using primitive gates and switches. There are continuous assignments using Verilog operators. So continuous, uh, using Verilog, one of the things you can do is use continuous assignments, and using those continuous assignments, you can build a netlist of gates, primitive gates or switches which are interconnected with each other. It's like a schematic design basically. It's a netlist. Schematic always consists of netlist, and the structural design it consists of a netlist. Whereas behavioral design or behavioral modeling of Verilog is done by functional description. We describe the function of the circuit in Verilog using syntax, Verilog syntax. Then it has timing controls and concurrency specification. So there is a way to develop concurrent logic in Verilog. We would do that in behavioral modeling, and we can develop timing controls also for clock and other things. To do this, functional description and concurrency specifications, we have something called procedural blocks. There are two types of procedural blocks in Verilog: always block and initial block. We'll see what this means. And obviously, there are registers, latches. These are examples of sequential logic. So we'll have sequential logic circuits. We'll have combinational logic circuits. We could have primitive gates if required also in the behavioral description. All of this put together will create a behavioral model in Verilog. So we describe the function using all of this. In structural description, we create a structure of the design using a netlist approach. So if you take Verilog as a hardware description language and try to have an analogy with something like a C programming language, so what we can really conclude is a programming language like C plus timing controls plus concurrency specification can give you a hardware description language. Okay, so what is lacking in C language? People might ask, why don't you use C language? Because C language was around when Verilog and VHDL were developed. So these two things were lacking. timing controls and concurrency. You still cannot have clock control in C language. You cannot still have concurrent logic execution, parallel logic execution in C language, even though they are trying to develop other languages for that, the logic. So that's what a hardware description language gives me. Programming or functional description plus timing control plus concurrent. Okay, any questions?
No.
No.
Simple example, if we take this procedural statements, there are various procedural statements which describe the behavior of the design. So we have like always block, always is the procedural block. Always add some event expression. So this is called the sensitivity list of always block. Means any signals in this expression or in this assignment, the always block is sensitive to this events on number signals. So there are, let's say, two signals in this bracket. Any change in the signal value will trigger the always block. That's how the always block works. And you can have multiple always blocks in a Verilog design. We can have conditional statement like if then else. Inside the always block, we can have this various statements: if then else, for loops, while loops, or case statements, or any other logic description. It could be behavioral or sequential logic description. And basically, the basic building block of Verilog is a always block and initial block. So using the always keyword, this is the way it works. Is if you take this simple design for this simple piece of Verilog code, always at activation list. This list could have one or multiple signals in it. Any change in the signal value and this always block is triggered for execution. Begin the always block. So anytime you have a always block, you have a begin and end for that block. If x is equal to y, then out gets in 1, else out gets in 2. So this is we are comparing x and y, some signals. If they are equal, out gets in one value, which is let's assume input 1. Else, if they are not equal, out gets in 2 value, which is some input 2. So this is a comparator. Based on the comparator, output will be assigned. This could be the always. This is a simple case of always block where any change in the signal values, only that any change in the signal value will trigger this always block. If there is no change in the signal value, the always block will not be triggered. So if you have always block and we have delays, it could be slightly confusing the way it works. Let's take two examples. Suppose you wanted to wait 10 delta cycles. So let's assume there are 10 time units. And after an input changes, we wait for the 10 time units and then check if phi signal is 1. If then, and then you update the output. So there are delays. You can take two examples of delays. Always at phi or in. This is my sensitivity list. Any change in phi signal or any change in signal, this always block is triggered, which means this line will be executed. Inside the always block, what do we have? Hash 10. This will give me a 10 cycle delay or 10 time unit delay. Hash 10 will give me that. If phi means if phi is equal to 1, then out gets in. The second example, the similar example, always at phi or in, sensitivity list stays the same. If phi, I check my signal first, then hash 10, wait for 10 cycles, 10 time units, out gets in. In the first case, there is a delay, then you check for the signal, then output is updated. In the second case, you check for the signal, then there is a delay, then the output is updated. Okay, so if this is just, let's assume, forget Verilog for now, just use your logic for the time being. In the first case, when will the output be updated, after what time delay, and in the second case, when the output will be updated or after how much time delay? Can you tell me? Just apply logic. If you don't understand Verilog for the time being, for example, just forget that and just apply logic. In the first case, output gets 10, assume that it is nanoseconds. So let's say each time unit is nanoseconds for now. Just assume it's nanoseconds. Output gets updated out after how many nanoseconds in the first example, and output gets updated after how many nanoseconds in the second example.
After 10 in the first case and in the second case?
First case is how much? Sorry,
10?
10. Okay, and the second case?
Uh, is it 1 or maybe 10? Also 10?
Also 10. So that's your answer, right? Okay.
Mm-hmm.
Let's wait for Anirudh's answer.
Okay.
For the first one, if it's only 10, then it will give an output. For the second one, if it's between 1 and 10, then it will give an output.
First one is after 10. So it cannot be between 1 and 10. It has to be some specific absolute value. It cannot be a range of values.
So,
So
uh,
it could be 1 or
for the
2 or
first one,
3
it's
or
10.
whatever. Okay, first case is
For
10.
the first one, it's 10, and for the second one, it should be 1.
It should be 1.
Mhm.
Okay. So why is uh, I will so first you explain why you think first one is 10 and the second one is 1, and I will give the same chance to Ruth to explain her answer. Always at 5 or in first case, right?
Yeah.
So how do you apply the logic and say first one is dated after 10? So we are just dealing with simple logic here, right? In both cases, it's just represented in Verilog format. Ruth, can you explain? I mean, what is your why did you come up
Yeah.
with 10 as an option?
Yeah, because we were first waiting for 10 delta cycles and then checking the value of 5 and then getting the addendo and out equals in.
Yeah.
That's why I said, because we're first checking, first doing the time cycles and then going
Okay, in
and
the second
checking.
case,
And in the second case, I said that was going to be 10 too, because we were checking and then waiting 10 cycles and then getting the value. So that's why
okay,
I said that. Or, yeah.
okay, so you are assuming that the phi changes immediately, right?
Yeah, assuming that. Yeah.
Okay. How about you, Anirudh? Second case, first case
I
10 is
say
okay. Second case, why is it 1 in your view?
uh, I say that the phi changes immediately after one cycle. So
Okay. So in
that's
this
why I said 1.
So in the first case, 10 is pretty much simple. The second case is if phi changes immediately at zero time. Let's assume phi changes at zero time. So there is no delay getting, we are not consuming any time period here for checking in, the phi not consuming any time from changing to 0 to 1. Then, so if phi is 1 immediately, then you wait for 10, then out equal to n. In the first case, you wait 10, then check for phi, again which will consume 0 time, then out equal to n. So out equal to n in first case is after 10. Out equal to n is after 10 because phi is updating in 0 time. Also after 10. Both cases output or out gets in after 10 nanoseconds because we said that the time unit is that. So depending on the delay and depending on the signal that you are working with, this might change in case the phi is going high after some time. Okay, so if I say phi will is 1 after 10 nanoseconds, another 10 nanoseconds, then this 10 plus this 10 will give me 20 nanosecond delay here, this 10 plus this 10 will again give me 20 nanosecond delay in case phi is going to get delayed updation. So in the earlier
Mhm.
case, we were assuming phi was getting updated immediately without any delay. So those it's 0 nanoseconds here. 10 plus 0 will give me 10. Out gets in after 10. Phi gets updated in 0. 0 plus 10. 10 gets out gets updated within after 10 nanoseconds. So this is how it will work. So this is the kind of thing that works in hardware, because hardware, any input can change randomly at any time, and your output should be calculated based on those input combinations. So this is something that you have to look at. Okay.
Yep.
Okay.
There is something called, this was always block. So we also have something called initial block in Verilog, which is called another procedural statement, a procedural block. All the Verilog code, or most of the Verilog code that is behavioral, is that goes into a always block or an initial block. So, but there are certain rules for an initial block. So initial block is also a procedural statement, but it does not need an activation list. It will run just once when the simulator starts. So Verilog was actually developed, as we have seen earlier. It was developed only as a simulation language. It was only afterwards in mid 90s or late 90s when synthesis tool was developed and Verilog could be converted to hardware. So when initial block will run only once when simulator starts, as far as simulation or software simulation goes, or it will run once when the hardware design starts or hardware design initializes. So initially, when Verilog came out, it was not synthesizable, so it was not meant for implementation. But nowadays, I mean, many years since now, before now, initial block can be synthesized and logic can be implemented on a FPGA or hardware ASIC. It was used mostly in testing purpose earlier. Nowadays, it can be used for testing and design purpose. In the simulation environment, it is used to initialize the simulation environment. So again, I'll ask you a question. Now, since this initial block, one of the key rules is it will run only once, either when the simulation start, as far as simulation goes, or if you're going to work in hardware, it will run once when the hardware starts. So, can you think about a reason why you need initial block? So, whatever you are doing in Verilog is Verilog is a hardware description language. So, everything that you declare in Verilog is ultimately going to get converted as a design either on FPGA or ASIC device, right? So it is meant to be converted to hardware later on, down the road. So whatever you provide in Verilog, there should be some reason or something. It should be useful for some purpose on the hardware. So can you think about initial block? Why would I need something like an initial block, which will run only once, not again? So initial block can have multiple statements, like always block. It can have one or multiple statements. So I can include as much logic as I can inside the initial block. But the requirement is, or the condition is, it will run only once when the simulator starts or when the design starts. Why would I need something like that in hardware, as far as hardware goes?
Do you want to reset the clock cycle before you begin
Do you want to reset the clock
using?
cycle? Can you elaborate that or maybe put it in a different way?
Maybe a block to begin with?
Why would I need that block to begin with? There should be some purpose for that in hardware design. Have you guys used any boards at any point of time, like embedded microcontroller boards or even FPGA boards in your lab anytime?
Yeah, I've used microcontroller ports.
Microcontroller
Me
board,
too.
right? So typically, what are the main components on that microcontroller board? Can you list down the main components involved? Typical board.
Power supply, reset, uh, ground, input output pins.
Right, I mean just a component level. So microcontroller is one chip that you have, then there is a power supply section. What else?
Interfaces, USB, HDMI.
Those are the ports, right? Those are the interfaces. Anything else? So normally when you turn on the microcontroller board or when you power up the microcontroller board, what happens? What do you see there?
Um, you basically switch it on and you see a LED blink showing that, indicating that the board is on.
Yeah, so that could be one of the things that happen that when you power on the board, there is some LED on the board which will blink once or twice, or there is some pattern that it will blink in, showing that the board is on and it is in healthy state. It is okay, right? So what happens? How do that LED? How does that LED blink? Let's assume that LED blink five times. How does that LED blinks five times?
The basic program that it has to do when it starts up.
So what would we call that condition as?
Initial conditions or
A reset
reset
condition.
conditions.
Reset condition, right? So when you power up the board goes into a reset state. On reset, there is some program that gets executed. In this case, let's assume the program is blinking the LED five times, on off, on off, on off. So there is some logic that I have to execute on the board on reset. If I want to do similar things on a FPGA board, let's assume that I have a FPGA board from some vendor and I turn on the board, I power up the board. Let's assume there is a LCD display there. Along with the LEDs, there is a LCD display. And normally in such cases, what they will do is it will show some basic message that uh, from typically the name of the company who's providing the board, welcome or something like that. There's some message displayed. If there are some LEDs, they will blink as you said in a particular pattern. If there are, let's say, five LEDs, all the five LEDs will blink one after another. Something like that will happen. Where does that logic go? That logic is where this initial block will come into picture. When you power up your design or you power up your board, it has to execute some logic. So if you consider that and apply that within a chip, now that is at a board level. Let's say I want to do some initial logic execution when I power up my chip. That has to go somewhere, right? When the logic that gets executed on power up or reset condition, that's where the initial block will come into picture. All the logic that I need to execute on power up, I can put it in the initial block. When I reset my system, the initial block will execute its logic and then it will go to the rest of the design after that block execution is over. Do you understand this concept of initial block where it could be used?
Yes.
Yes.
Typically, if you have any memories, okay, any memory has to be initialized to some value. It could be 0 or 1. Every bit I mean. That initialization part of the memory will always go in the initial block. So when I power up or when I reset my system, my memory gets initialized. Or the other option is I have to blink some LEDs to show that the board is in OK status. All that logic will go in the initial block. Building similar things. That's where I need the initial block in hardware. So if you want, you can just note down these couple of points and then we proceed. Okay.
Okay.
Yes.
Uh, we have something called hierarchical modeling concepts. So we can develop a model or a design which is hierarchical in nature. So if you look at this simple example in front of us, the top level of the design is the system level. Below that, there are two components or two modules, comp 1 and comp 2. Under comp 2, we have sub 3. So this creates a whole hierarchical design. Sub 3 is a component or a module under comp 2. Comp 1 and comp 2 are modules under system, which is the top level of the design. Each is represented by a module in Verilog. In Verilog, everything, each design, each of this becomes a separate design. One, two, three, four. We'll have four modules or four different Verilog files, one for each module. Sub 3 will be a separate module, Com 2 will be a separate module, Com 1 will be a separate module, and system will be a separate. And the module will have logic related to that particular level of design. Com 3, Com 1, Com 2, Sub 3, and system. And each module can have its own ports, input output ports, which will help us connect between various modules together. Using this approach, we can build a hierarchical design. There are two types of hierarchical designs we can build. One is called top-down design methodology, the other is called bottom-up design method. Top-down means we start from the top and we break it down into sub-blocks, and then the sub-blocks are developed, further sub-blocks. In bottom-up design methodology, we develop the bottommost components or the modules first, then one level above, and then finally the top level, which will integrate all of these modules together. So this is a hierarchical design concept, and using hierarchical design, either I can go top down, I can go bottom up, depending on what kind of design methodology is used. Typically, we will go bottom up because the lower level modules are designed first, and then the top level module will be designed. That depends again on your team that you are working with. Some team might prefer a top down design methodology because all the design specifications for each block is predefined before we start Verilog design. And then typically what happens is nowadays it's very common that you'll have distributed teams, right? So let's say this entire thing is consists of entire one chip consists of this entire blocks. So what we have to do is we have to break down the design, and it is assigned to various teams and team members. So let's say one team is developing these two blocks at the bottommost level, leaf cell. There are four teams developed. These eight blocks at the bottommost level is distributed across four teams. And then there's four blocks, two each is goes going to some other team, and finally one team is developing or integrating all the blocks together. So what is communicated between the blocks is predefined, where we call it as a design specification. And that design specification goes to each and every team, and each of the team has to follow that. So they know what comes in as input to the block. Let's say I'm designing this block. I know what is coming in as input and what is going out as output to some other block, and I have to follow that design specification and design, and based on that, I will do my design. If everybody does that, if everybody follows the design specification, the top level guy, let's say somebody is doing a top level integration, he can develop a top level block where he will take all the inputs from everywhere, and it will basically be interfaced. So this is a top level integration. So some design, let's say there is some data that is coming from this leaf cell and going to this leaf cell. So how does it travel? This leaf cell, subblock 1 top level, subblock 4 this leaf cell. That's how the data will travel. So the top level integration will do all of this, and that will also be done parallelly. So we can do it that way, or we develop first all the bottom level blocks in the bottom up design methodology. Then we develop one level above, the modules one level above, and then finally we do a top level integration. It depends on the team that you are working with. Somebody like a system architect or somebody decides how we go about it and what is our design specification. But this is basically how you develop hierarchical modules or hierarchical designs in Web. Okay. Any questions on the basic concept?
No.
No.
So let's take module. So module is the basic building block in Verilog. Anything that any design in Verilog will have a module and end module. Everything goes in between for that particular module. Modules can be interconnected to describe the structure of your design. So as we saw here, hierarchical thing, each of them will have a module, and then they will be interconnected to some other modules using the IO pins or input output pins. Modules always start with a keyword called module and ends with a keyword called end module. So you have to remember that Verilog is a case-sensitive language, unlike VHDL. VHDL is case-insensitive, but Verilog is case-sensitive. Means this keyword called module is a lowercase keyword. If you type in module in uppercase, it will be different. Module in lowercase is a keyword, but it's always good to not use it since module is a keyword, lowercase or not. Don't use it for module declaration. The name of the module should be something more synonymous with your design. So it has to be, if this is an AND gate, you can call this module as AND or AND2 or AND3, whatever your AND gate is. If you're developing a processor, your module could be CPU or CPU top, for example, if it's a top level design. Then followed by the port list and then end module. So modules have ports for interconnections. Wherever I put some part is going to get okay. So modules always have ports for interconnections. We'll see as we go forward. So this is a simple two-input AND gate. How do I model this two-input AND gate using Verilog? Module ports are similar to the pins on a chip. They will help us communicate with the outside world. The pins or the ports can be input, output, or in-out, which is bidirectional ports. So knowing that, let's say I want to implement a simple two-input AND gate using Verilog, where one input is called I0, the second input is called I1, the output is called O. Verilog for that AND gate is what is mentioned here. Module and 2. And 2 means it's a two-input AND gate. I can know it's a two-input AND gate. Followed by the port list I0, I1, and O, out of which I0 and I1 are single-bit input ports, each of them. O is a single-bit output port. Inside the module, I have a assign statement, which is called a continuous assign statement. There is no always block here. This continuous assign statement, which is helping me implement the AND gate design. O is equal to I0 and I1. This AND sign will know me, they will know, or the synthesis tool will know that I'm trying to implement the AND gate using this continuous assign statement. Where O output will get I0 and I1 end module. This two-input AND gate can be modeled in Verilog using a continuous assign statement in this fashion. Okay.
Yeah.
Using a two-input AND gate. Yeah, sorry, Anirudh, any question?
No.
Using a two-input AND gate, two of them, I can create a three-input AND gate. So that is where hardware design concept comes in. We'll see how it is working. These are two-input AND gates. What we're doing is the first two-input AND gate, there are two inputs, I0 and I1. And the output of the first two-input AND gate is connected to a wire called temp. We'll see what that means shortly. This output is connected to the input of the second AND gate, this first input. The second input of the second AND gate is connected to the top level I2 input, and final output is generated here. So what we're doing is using two input AND gates, I'm creating a three input AND. So how do I model this? I instantiate. The concept is of module instances. Or I create instances of two design in the top level. So this is my top level module called AND3. This is my port list. There are three inputs to AND3 and one output. I0, I1, I2, and O. Out of which I0, I1, and I2, each of them is a single bit input port. O is a single bit output port. There is a wire called temp. Wire because I'm going to connect. This wire is literally a wire. So wire is a data type in Verilog, which we'll see later on. We'll connect this point to this point. So there is a wire called temp which will connect this. Then I'm going to instantiate. So the terminology is instantiating gates. I'm going to instantiate and to gate two times. What that means is I'm going to create two copies of the gate. Instantiation means two copies, creating copies of that gate. I create two copies of the gate. Each copy is represented by a separate instance name. One is called A0, the other is called A1. So I can differentiate between them. A0 is this one, A1 is this one, this copy or this instance. Now each of those gates AND 2 is represented by this module. So this module of AND 2 is separated. What is the input outputs of AND 2? There are two inputs and one out for the basic AND gate, which I'm going to instantiate here. So I0 of the AND2 module is connected to I0 of the AND3 module. I1 of AND2 module is connected to I1 input of AND3 module. O, which is the output of first AND gate, is connected to wire temp. Now second instance of the AND gate, which is denoted by instance A1. I0 of the second AND gate is connected to I2 input of the AND3 module. I1, which is the second input of the AND gate, AND2, is connected to temp here, this connection here, this input. And O, which is the output of the second AND gate, goes to the final output. We call it as a primary output AND module. So using two input AND gates, two of them or two copies of them, I have created a three input AND gate by using module instantiation method. This AND2 design module is separate as described here. This AND3 module is using the AND2 module twice instances of this module and then creating a bigger module. This is how you create hierarchy in Verilog, or bigger designs. Is it clear? Do you have any questions? Hello?
No. Sorry.
And this concept of module instantiation is very close or very similar to C++, which is object-oriented language. It has a concept of classes and instances, or classes and objects actually. So just to
Mhm.
give you an analogy of that, not that it is required, but if somebody has a background in C++, which is object-oriented language, module will be similar to a class, instance will be similar to object. Anirudh, clear? Any questions?
No.
So please note down these two slides and then we'll go forward, just for your reference. Then
Yeah.
Yes.
next slide. Right?
Yeah.
Yes.
Each module will be a separate Verilog file. So let's say this will be called and3.v. And3.v will have this module. This will be a separate Verilog file. Let's call it and2.v. So this will be a separate, each module should have a separate Verilog file. This will go into, let's say, and2.v. This will go into and3.v. And when you simulate your design, you should include both and3 and and2 because both are part of the hierarchy. Okay, so we have something called data types in Verilog. So what are they? There are three data types: nets, registers, and parameters. Net data type represents physical connection between structural entities. So net data type uh, is basically a physical connection between 2 points. A net must be driven by a driver such as a gate or a continuous assignment. Verilog automatically propagates new values onto a net when the drivers change value. So this net data type we saw just now with wire temp. There's a physical connection between this point and this point. Output of this gate, input of this gate. There is a physical wire. Wire is of data type net. It is of data type net. There has to be one driver. This gate is driving value on the wire, which will then propagate to this point and transfer the value. The data here, logic 0 or logic 1 will travel the wire and go here, which will get accepted as input to the second hand. This is what this means. It's a physical connection. It has to have a driver, logic driver, such as a gate or a continuous assignment, and it will automatically propagate that value to the other side, the wire, the net. Second data type is called registers. Registers will represent abstract storage element. It will hold a value until a new value is assigned to it. Registers are used extensively in behavioral modeling and applying stimuli. So register is something that you typically have a requirement where you have to store a value for some time, and then later on, based on certain input requirements, the value might get updated. So where do I store it? I have to store it in a register declared by data type reg or register. Parameters are not really those are registers, and the third thing is parameters. The third data type is parameter. Parameters are like constants. You declare it once and then you use it multiple times. I think we saw one of the slides earlier. We call it as the parameterized design. That's one of the advantages of Verilog. We saw an example where we declare a parameter called burst width, and that burst width parameter is declared once and then it is used multiple times in the design. But wherever it is used by that label called burst width. So if I change the burst width, I have to only change it at one place and it gets automatically propagated throughout my design because I'm using the label called burst width. I'm not using a hard-coded value like 8 bits or 16 bits or whatever it is. Since I'm using the label called burst width, which is actually a parameter, I only declare it once and I use it multiple times. That's where parameters come into picture. So nets, registers, and parameters. Those are the three data types that you can use in Verilog. Then you have logic values. In Verilog, you can have your signal can have one of the four logic values. 0, which is logic 0, 1, which is logic 1, X, which is unknown, and Z, which is high impedance, or unconnected, or tri-state. Typically speaking, you should never have X in your design. If you have a X in your design, there is some problem somewhere. It could be multiple problems, which we'll see later on. Your design or your signal can be logic 0 or logic 1, or in certain cases, high impedance, Z value. Typically, high impedance cases, the Z value is allowed when you're dealing with a bidirectional bus or a bidirectional signal. When you're dealing with a bidirectional signal, the direction that is currently used is normal, is it could be logic 0 or 1, but the other direction which is not used will be tri-stated or it will be in high impedance state to ensure that the data is not flowing out the other direction by mistake. Typically, high impedance values or tri-state values are used for bidirectional ports or bidirectional pins. So a logical value in Verilog can be one of these four values, technically speaking, but it can never really be x, because if it is x, it can never be in your design can never be in an unknown state. It has to be in a known state all the time, whether it is logic 0 or logic 1. Even high impedance is a temporary state. Ultimately, it will move to logic 0 or logic 1. So ultimately, your design should be in one of these two states, logic 0 or logic 1. If it is not, your design might become unstable. Okay, any questions?
No.
No.
Yeah, so nets, as we saw, are physical connections between devices, and wire is one of the types of nets. Registers is using implicit storage, so we declare it and we store the value. A register data type is denoted by a keyword reg. Reg and wire both are lowercase keywords. An integer is also we can also use a data type called integer. Internally, it's a register, 32-bit register. But we can directly integer is like a special register, 32 bits, and we can declare a data type of called integer, which can hold integer values. So typically wires are of data type net, and we can have from a Verilog language perspective, this can be the number of wires or the type of wires that can be part of your model. It is wire or tri or WR tri-or, which is wired or tri-state or. Wire is normal wire, tri is tri-state. WR is a wired or tri-state or wired and tri-state and some of these other things. If you remember, we saw that only some subsections of Verilog are synthesizable. That means I can convert that Verilog to working FPG or a working ASIC in hardware. The other part is only meant for simulation or testing purpose. Wire and try is only meant for design purpose, for implementation. The rest of the stuff is only meant for some specific testing purposes, not to be implemented on the FPG. So as far as FPGA or ASIC design goes, we only use wire or try, even mostly wire, not even try in certain cases. So net means wire, or in certain cases maximum try or try states. The other stuff we don't use for design purpose because they cannot be synthesized on FPGA or ASIC design. But it is there as a part of Verilog language. Reg is a register data type which will hold a value. Integer, as we saw, is a special type of register, but it is we can have a separate data type as a data type as integer, which is internally a 32-bit register. So we can have a signal being declared as an integer which can hold integer values. Internally, the synthesis tool will implement a 32-bit register for this integer value. We have something called time as a data type also, which can hold 64-bit unsigned numbers. We have something called real as a separate data type. Real can hold real numbers or fractional numbers. And then we have real time, which can hold fractional number of times. So fractional number of times could be 10.1 nanoseconds, 30.20 nanoseconds, so whatever fractional time value. Time is will hold unsigned 64-bit number, real fractional numbers, and real time fractional time numbers. But all these three data types mentioned last, time, real, and real time, are not synthesizable. They are only meant for simulation or testing purpose. So you can use it in a test bench. We can write a test bench. We will be writing a test bench to test our design. In that test bench, and the test bench is never implemented on the chip. So for the test bench purpose or testing purpose, I can use this data type in my test bench, Verilog related to the test bench. But my Verilog related to my design, I cannot use it because it is not synthesizable. This too is synthesizable, regular reg and integers. Okay.
Mm-hmm. Yep.
So how do we declare a net or a register? There are some examples given. Net, as we know, is represented by wire in Verilog. So wire examples are this: wire W1, comma W2. W1 and W2, each of them is a single bit wire, which is internally a data type net. Wire W1, so this can be represented in two separate lines also: wire W1, wire W2, or in a single line. These are single bit wires. If you say wire 7 down to 0, W3, means W3 is a 8-bit wire. 7 down to 0 means 8 bits. 7 is MSB left hand side, 0 is LSB right hand side. Okay, this is a 8-bit wire. If you declare a register, how do you declare that? Reg R. R is a single bit register. If you declare a register called vreg, reg 7 down to 0, vreg is an 8-bit register, 7 down to 0. So when you want more than 1 bits, you have to declare it in this fashion. This is 8 bits. If you want to declare a 4-bit wire, for example, I can say wire 3 down to 0, W3. If I want to declare a 5-bit register, I can say reg 4 down to 0, vreg. 4 down to 0 will give me a 5-bit register. When you say something down to 0, have you come across in your, did you have processor design as a part of your curriculum for your undergrad or grad curriculums? Anytime microprocessor
No.
design or microprocessor architecture as part of that? See, for microprocessor, typically for microprocessors or even microcontrollers, because microprocessors are part of microcontrollers, we have two types of systems. If you recall, it's called a little endian system and a big endian system. Okay, a big endian system. This what we represent here is a little endian system. Means on the right hand side is the LSB value, the little endian system. The left hand side is the MSB value, the big the so that is how a little endian system goes. If I would have said 0 to 7, it's also 8 bits, but 0 to 7 rather than 7 down to 0, if I say 0 to 7, it's a big endian system because on the right hand side is a bigger number. That's a microprocessor architecture language. Little endian and big endian. This is a little endian system. Endian means the spelling for that is ENDIAN, Endian system. This is a little endian system. 7 down to 0, 7 down to 0. I declare a multi-bit wire using this format. I declare a multi-bit register using this format. Okay. And I can also declare a memory. Memory is internally a register because it has to hold values till a new value gets updated. So how do I declare a memory? Reg 7 down to 0, my memory, which is the name of the memory. 0 to 1, 0 to 3. So how does this work? Any memory. Now, if you recall digital logic design, what are the two things a memory has? How is this? How is the structure of the memory? Can you tell me? Can you recall that? When you define a memory, there are two things you have to take care of from a memory structure perspective. What are those two things? Or how will you define a memory? In this pure logic form.
RAM and ROM.
Those are the types of memory, right? Let's assume we are dealing with a RAM, which is a read-write memory, random access memory. So how will you define when you want
Clocks.
to define a memory? What is that? So when you decide to define a memory, you say I want. You have to have something in your mind. Like what is the size of the memory? Right? How much memory do you want, and how will you define it?
Depending on the size.
Depending on the
Or
size. Yeah, you just assume some size. Okay, let's assume you want a 1 KB memory. How will you define that? 1 kilobit memory. So memory is a structure, right? It's a digital logic structure. It's a digital logic circuit in a way. And there are certain aspects to it. How do you define that? That is the part I'm trying to get at. Verilog is just a language, right? Verilog is just a language that we are using to design digital circuits. It could be combinational or sequential. You recall? No?
No.
Okay. Is Anirudh also start? Yeah, I think he just called back, logged back in. Is it? Hello,
Yeah,
Anirudh?
I just
Okay.
yeah, I had a drop call.
Okay, yeah. So any do you recall we saw that when we did the digital logic design overview?
Uh,
Okay. So I'll tell you, memory, so when you define a memory, the memory is basically what it has a width of the memory, there is a depth of the memory. What is the width of the memory? Width of the memory means each location. Depth of the memory could be, let's say, 1,000 locations, 250 locations, whatever that is. And each location is some X number of bits. And we stack X number of bits, let's say 8-bit memory. If we stack 8-bit memory one on top of another 250 times, my depth becomes 250, my width becomes 8 bits. Each location becomes the width of the each location becomes the width of the memory, and the number of locations, such locations, becomes the depth of the memory. Each memory will have a width and a depth. So let's say I want to design a 1 kilobit memory. The width of the memory is 8 bits. So how many such locations I would need?
1 kilo,
Bits.
1 kilobits.
Right. So I would need 125 locations, right? To create a 1 kilobit memory. Each location is 8 bits. If I have 125 locations, 125 into 8 will give me 1 kilobits. Each location is 8 bits. I copy this 125 times, one upon one below another. That is how my 125 locations will come. So 125 into 8 will give me 1 kilobit memory. So what? So keeping the calculation aside, each memory will have a width and a depth that you have to work with. In this case, the first part is the width, 7 down to 0. The last part is the depth, 0 to 1023 means it has 1024 locations, this memory. And each of the 1024 locations is 8 bits wide. So 1024 into 8 will give me 8000 something, which is roughly a 8 kilobit memory. Okay, that's how I will declare my memory. Each memory will have the depth or the number of locations, and each location will be having a certain width, X number of bits. That's how I will define my memory very well. Anything that starts with two forward slashes from this point till the end of the line is a comment in there. If it starts here, from this point in the end of the line is a comment. This point in the end of line is a comment. So do you understand how the memory got declared? Or any questions, any doubts related to that?
Uh, no, now it's
No.
clear.
Clear?
Yeah.
So this is how you declare wire single bit or multiple bits. This is how you declare register single bit or multiple bits. And this is how you declare a memory in Verilog. Depth and width of each location. If you want, you can note down this slide. Okay, done?
Yeah.
Yes?
Yes.
Okay, so we'll stop here today and next time we'll continue on Monday. Okay, next lecture will be on Monday.
Okay.
Okay, yeah, bye bye.
Okay.
When